Hello. I've been away for a while. Today we'll start simple harmonic motion. Simple harmonic motion is one of the most important concepts in physics, and you should learn it very well. So there are several different ways you can look at it. So let's look at the most direct way. So we look at one-dimensional. We're going to look at one-dimensional situation. And in one-dimensional, what we mean is there's one variable whose dynamics we want to study. So that means one variable, which can be kind of denote by letter X. It can be this can represent some property. For instance, when we have like a spring and a mass system, and so this is frictionless. So this is a system. So in here, the way we describe X is at some point there is no force on it. So there is a place where we no force when block here. So of course there's a gravity and there's a normal, but no force, horizontal force. That's what I mean. No net horizontal force. Of course, there are no net vertical force also here. So this, if you call this position origin of the system, coordinate system, and you say when it extends, this side is positive X, then at some point, this spring is stretched all the way here. And at that point, the coordinate of this point is x of t. So this is the variable in this situation. And you may already know that the block will kind of oscillate between some limit, right? So that's a motion. That's we'll say that's a simple harmonic motion in this case. We'll see what the simple and harmonic means here. So it just oscillates. That's much you know. Actually, it turns out this is not the only one. You may also be familiar with this other system where also, but it requires some caveats. So here is a pendulum, a simple pendulum, and we're gonna swing it in this way. And so we say this direction is theta equal to 0, and if I measure this side, theta is greater than 0. If I measure that side, theta is less than 0. So that would be, so at some other time, this thing is over here, and I'm measuring on the right side, so some theta of t, this will be positive. And if this angle is not too great, and so if I limit myself to small angle, that I'm going to be only swinging between this. So if this is say about 15 degrees or something like that, then I would be good up to like 2 decimal places. So approximately, if we say theta is small, and in radian, so this is also a variable, so I don't call it x of t. So this is what x of t is here, this angle in radian. And this angle actually is also an example of a simple harmonic motion. So the way this changes also is simple harmonic motion. So let me see what the simple harmonic motion will be. It's like in this case here, with time, the value of x of t, can be described as a combination of sine and cosine. So like a cosine and an angle here that depends on time, and usually I'm going to write like this and be exactly same omega t, and a and b depend on how I started it. Did I kick it to get started? I pull it and let go. There are various ways I can start it, and they correspond to different a's and b's. Another way simple harmonic motion solution, this is called solution, is described as you can combine these two constants, don't have to be part of cosine and sine. You can just write one cosine, but you have to include a phase angle. So let's call it, this is A1 and this is B1. And so another way is A, some A, which is not A1 and B1, but it's actually a combination of them, omega t plus phi. In this way of writing, you have these two are depend on how you got started. Well, of course, you could write yet another way. You could write some kind of B sine omega t plus maybe some other phase angle. And it turns out this A and B will be the same, so we just write down A, same. And this is the phase angle. This phase angle that goes with the cosine, this phase angle goes with the sine, and they'll be off by 90 degrees. You can actually prove them by expanding and things like that. Now, why are these guys, this problem same as that problem as far as simple harmonic motion thinking goes, is that if you look at here, theta of t is exactly this way also. Theta of t is going to be similar. Okay. Okay, so what makes a simple harmonic motion? So what makes a simple harmonic motion? So let's look at energy. Okay, let's look at energy. A lot of people look at force, but let's look at energy. So, and we can look at this system, and so this is my reference, and over here at time t is over here, and this is the reference O, and this is the x of t. Okay. At this time, it's got some velocity, so you have a velocity will be just x coordinate, so v will be dx dt. So let's mass be m, the spring constant be k. So if you ever studied a spring before, you know when the spring is stretched by this amount is x of t. So the length of the spring doesn't matter, right? It's the change in the length. So you have a kinetic energy, and then you have potential energy. Kinetic energy will be just coming from the velocity and mass, but potential energy will be all in the spring, right? So this will be half k times amount change in length of the spring square. And this whole thing is what we are calling x here. So this is just a half kx square, and this one is half m dx dt square. So whenever you have energy made of two square terms, half m dx dt square and half k x square, this is the same variable as that. Whenever you have that, so this is typical of all, this is the typical of all systems that exhibit simple harmonic motion, SHM. Okay, is that really true? How about is that true? Let's check the pendulum. Okay. So checking the pendulum, let's see. You have a this is the reference direction. At some point is there, it's L, and so this is theta. So what's this speed? Well, you can use a polar coordinate, and you have a L d theta dt will be the speed, and so this will be this square half m, that will be the kinetic energy. So this is mass m, so this is the kinetic energy, and potential energy will be well, let's see, this is the reference 0. Then we need to figure out this height, plus mgh. What is h? H will be this whole thing is L, and subtract L cosine theta. So h is L minus L cosine theta. Well, this looks nothing like that. You know, this is my x, and so this can be made to look like that, but this one, it doesn't look like a square. So except when this is only true when theta is less than very small, theta very small. So we can do a Maclaurin expansion of this. Maclaurin expansion will be 1 minus theta square over 2 factorial plus theta to the power 4 over 4 factorial, like that, right? And we just keep these many terms, and that leads to h L minus L over 2 theta square. And this becomes plus, and you can see now we can arrange it to make it look like that. So this whole thing will become half ml square. So this is what replaces m there, d theta over dt square, plus mgl, half mgl, that becomes like a k theta square. You can see that this got two quadratic terms, a quadratic term of this type and a quadratic term of that type, and that completely becomes analogous to that. Okay, so that's how this is simple harmonic motion, only when the angle is small, and we can kind of keep only the leading two terms in the cosine expansion. Okay. The solution for this guy, if you remember, x of t was a cosine omega t plus phi. That's one way of writing, right? And I didn't say what omega was at that time, but omega in the simple harmonic motion is actually ratio of these two. Omega is equal to the square root of k over m. and this is angular frequency of the periodic motion. So you can see this is a periodic function, and from here you can actually relate to the period. So it's like it's 2 pi over time period. T is the period. A lot of these, when you try to solve simple harmonic problem, these equations and these formulas will become very useful. So you can see what omega is from this. So omega square is ratio of this over that, whatever multiplies that. So half k over half m, and half got cancelled out. So we do it over here. What's the omega for this guy? So this will be theta of t will be equal to sum a cosine omega t plus some phase angle, right? And what's the omega? So omega square is the ratio of this over that. Ratio of this over that. Things that multiply the quadratic, okay? So we have a half mgl divided by half ml square. Half cancel, m cancelled, one of the, so this is g over l, and so omega squared with g over l, taking just positive because frequency, and it's going to be 2 pi over time period. So you can see time period for a pendulum is, you can 2 pi square root of L over G. You probably know this formula, and you can see that this is only true in this small angle oscillation of a pendulum. So many systems are like that, and what we have done is what is called simple harmonic motion without damping. Okay, so to recap, so if you have energy is equal to half m dx dt square plus some half k x square, then this would mean it is simple harmonic motion, and x of t will have a cosine omega t plus phi with omega equals the square root of k over m. Okay, and so this is undamped simple harmonic oscillator. Okay, so there is a this was energy picture, but you can also do what is called force picture. So in the force picture, we look at a spring force instead of so this from here at some time t, it's over here, and this is x equal to 0, this is x, and this is xt. So at this point the spring is stretched, which means the spring force is this way, and so if you look at its x motion, so F equals to ma, and you look at just the x component, so this x component, positive x is that way, so this will be minus kx equal to m d square x dt square. Now this is a differential equation, so you can see d square x dt square equals minus k over m x, and you can convince yourself that if you plug this in here, then this is a solution. So that will means x of t can be written as a solution cosine omega t plus phi, and where a and phi are constants. Actually, this solution, when you think of this way, you can see how to get a and phi, and let me show you now. Okay, so I want to use this solution and show you how to get a and phi. So to get that, we look at what the velocity will be, and velocity formula will be just take a derivative of this, and it's going to be minus omega a sine omega t plus phi. Actually, this, if you work out here, you should work out here and then see how you can get these coefficients instead. So the way you get it is initial condition, meaning if I know this, so this will be given, and dx dt at 0 time is given. So let's call this v0, and let's call this x0. So if you work out what you expect from here, t equal to 0, put t equal to 0 here, so that means x0 is simply a cosine phi, and then over here v0 equals to minus omega a sine phi, just plugging t equal to 0 here. And I can, because these are given and these things are not known, so we can see one way to proceed. So let's look at it. Let's put omega on other side. So I have a cosine phi equals to x0, and maybe a sine phi equal to minus v0 over omega. Right away you can see how this will work out, right? You take a ratio, so like a tangent phi is minus v0 over omega x0. So that will give me phi. Another thing you can do is just take a square of this, add, so you're going to get a square, because sine square plus cosine square will be 1, will be x0 square, and square this guy will be 0 square over omega square, and a is supposed to be positive. This a is all the signs are taken care of using the angle here. So a is amplitude, which we think of as positive, so this a will be just a square root of x0 square plus v0 square over omega square, and the phi is minus arc tangent inverse v0 over omega x0. Okay, so this is how you get those constants. But you know, you can see also if v0 was 0, say over here, this is example will be like this. I let go, so I pull this, say k equals to 10 Newton over meter, and I pull this maybe 5 centimeter, and let go from v equal to 0. Pull this and let go. Oh, clearly you can see what's going to happen. Phi will be 0 because v0 is 0, and a will be a tangent of phi is 0, not necessarily phi is 0. Tangent of phi is 0, will mean phi is 0 or pi, right? And so, and a is going to be the square root of just x0 square, which is going to be x0, so this is 5 centimeter. And to decide between this, so to decide between these two possibilities, you can do something like this. So very next moment, the velocity will be pointed to that direction. It was 0, but very next moment is going to be pulled back in, right? That means dx dt is going to be less than 0 for t or very small. So if you look at that, dx dt minus omega a sine, let's call it some omega t is some epsilon plus phi, and this thing's supposed to be less than 0. So you can expand this, so it's going to be sine epsilon cosine phi. Phi can be 0 or pi. If it's 0, then it's plus, and it's pi, then minus. The other one will be cosine epsilon plus cosine epsilon sine phi. And in both of these cases, this is 0. So this is the one that's going to decide whether it's going to be less than 0 or not. So minus omega a, sine epsilon is positive number because it's very small. We can just call it epsilon is small, so just going to be some epsilon. Cosine phi can be. So if phi is pi, this will become positive because this will be minus 1. If phi is equal to 0, this will remain positive. So it's not going to be that, but it's going to be this. Okay, so that's how between we just get tangent of phi from this, and then we decide what phi will be consistent with the physical system we've got. Okay, we will do more problem later in this week concerning how to deal with the spring motion and simple harmonic motion. Okay.